All right, good morning, everyone. Welcome back. We have our usual due dates and important notes and such at the screen in case you need to grab a screen grab, pause, whatever on the replay. Write things down in case you miss them. All due dates are reflected in my math lab, etc., 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 and Canvas, of course. So you have your past chapter 4 homeworks that have not been due yet. There's their due dates. We did finish 4.4 last time. You are to read the next 1 to 2 sections per usual, so we'll be covering 5.1 today, so probably read 5.2, 5.3. I said I'm taking a pause on the Excels since we have our midterm coming up. We will get right back into those as the midterm approaches. Your project is due on the 21st. We discussed all of the details of that a week ago. If you have any questions, first of all, please go back and thoroughly watch that video. After that, if you have any questions, shoot me an email. The next discussion board that I'm going to post, I'm just going to keep this one related to the midterm. So I'm going to post a midterm discussion board today after class, and I'm not going to post anything specific about it. Remember that you have been provided your midterm review. It's in Canvas, and I'll point that down here. I know I said that once last time, but I didn't write it, so there's me writing it. And we'll get to that in a minute. But your midterm will be posted on July 8th at about 12:01 a.m. I'll have it up there before, but that's when it will get posted. And that's going to run through the 10th, so that is a week from today, roughly. So the 8th is that Wednesday, the 10th is the Friday. So you have next Wednesday through next Friday for the midterm. You get 2 attempts. I will take your best attempt. It's 2 hours, 20 questions. You're allowed a calculator. You will be provided a very, very, very brief, quote, formula sheet for the midterm. I'm not going to give you anything like that for the midterm review because you have the internet, you have your textbook, you have your notes, all of that good stuff. But as I said, on the actual midterm itself, if I have questions about time conversions, you need to know those. If I have questions like converting feet to miles or to meters or anything like that, I would give you those conversion factors, and you just have to know how to use them, whether it's going to be with dimensional analysis, out with the old in with the new idea, or using proportions. So again, the midterm review, I think this was 58 or 59 questions, somewhere in that ballpark. And I did mention to skip part of one of them in the title of Canvas, so make sure to pay attention to that. I think it was like 43, the second part. I may have said part B, and it's not actually labeled as part A and B, but I hope that you get the idea as a quantitative reasoning student. When I say part B, I mean the second question. So again, your midterm review is in Canvas. You get questions and answers. You are responsible for completing the in-between. Some of these questions are pretty easy. A couple of the questions are a little more complicated and extended, and that's kind of how you'd expect the midterm to go. Probably the majority of them are short, 2 to 3 steps, but then 1 or 2 are going to be a little more challenging. In particular, there's a question on the midterm review, I think, about candy that tends to throw people off more than others, and that's because of the types of units that they're in. But I don't want to spoil too much. Again, there is going to be a midterm discussion board for you to discuss that. You can ask questions. If someone says, hey, how do you do number 3? Then someone else can come in and say, this is how you do number 3. As I said, I might come in and help with those. I've been trying to keep the discussion boards pretty open-ended because if this was a normal class, I'd be, helping along with the discussions, but instead during class, I'm kind of dragging everyone along with me. So I feel like it's more appropriate, since I'm leading so much during class time, that y'all lead a lot more outside of class time for that. And it's not like I penalize you if you're wrong, so it's just a discussion. Okay, so with that being said, this is all the stuff that we have discussed so far, along with 1 or 2 minor, very new things, like the fact that the midterm review is in Canvas. It's a PDF file. I think I may have already made visible the formula sheet. I can't remember off the top of my head that you'll see for the midterm itself. I don't remember. Sorry about that. Anyways, it doesn't matter. So let's move on to chapter 5. So chapter 5 is all about what we call linear functions. Linear functions are called linear functions because their pictures are lines. Now, before we go into any of this stuff, I need you to understand the difference of a line and a curve, because the average person seems to think that a curve is a line and a line is a curve, or vice versa, something like that. When we talk about a line, lines are always straight, at least in the mathematical world. And if you want to just, talk, if you just want to talk to a normal person, a line might be a curve to them. But again, we're in a math class, we're in a QR class, so we need to go with the true definition of a line. A line is straight. So the phrase straight line is actually redundant. And this is where I would make a joke about a certain career and saying a redundant statement with them. But like I said, I don't like to make silly jokes when things are recorded. I'll make some jokes, but you know what I mean. I want to keep it clean. And that was a dirty joke. That sounds wrong. I don't want to sound insulting to a career. That's what I mean. It was all in good humor. I don't want to be misconstrued because it's a recording. So this is a line. Rambling aside, this is a line. It's straight. Now, lines are generally in a real math class represented with arrows on both of these ends. Admittedly, in a quantitative reasoning course, we don't always have the arrow on the left side, and I'll explain why that is as we get into some subject material. So that's a line. This is a curve. So you can see the difference between a line and a curve. Lines are straight, curves bend. It's like when you're turning in your car, you're going around the curve. Although some people interchange curve and curb. Been there, done that. A line, curve, straight, bends. Big difference there. So chapter 5 is all about graphing lines and some other things with lines. Now, lines are wonderful because they have a very, very simple algebraic expression for themselves. It's just a combination of what we call a variable term and a constant term. Whereas curves, when we try to express these things algebraically, they become much more complicated. You start seeing exponents with variables, things like x squareds and x cubes. You can even get into some weirder things that aren't what we call polynomials. And again, we're not really going into the graphical analysis of those types of things in here. We will actually do some light graphing with things that aren't lines later, but let's not put the cart before the horse. So plotting coordinate pairs, and you see this x comma y in parentheses. This has to do with what we call the rectangular coordinate system or the Cartesian coordinate system, which are one and the same thing. They're just different names for the same thing. So if you hear me say rectangular coordinate system, that is interchangeable with saying Cartesian system. And all that is you just draw a plus sign at first. A decent sized plus sign because you're going to be graphing on this. And then that's pretty much it. You label this horizontal line as an X, you label this vertical line as a Y, and then any point in this two-dimensional surface, this two-dimensional region, if I call this an A value and this a B value, that point would be A comma B. This is what we call a coordinate pair, and coordinate pairs are used to describe the location of any and every point in a two-dimensional plane. So think about my word file as a two-dimensional plane. I could describe the point here, I could describe the point here, I could describe this point here, I could describe this point here, all with just a pair of numbers. 3 comma 9, a 2 comma negative 7, a negative 40 comma negative 10 billion. One number, the first number tells you how far left or right you go. The second number tells you how far up or down you go. So this horizontal line that we labeled x, we call that the x-axis. And this vertical line that we labeled as y, we call the y-axis. And then any point, any location on that two-dimensional plane, and be glad we're not graphing in 3D, that's much more complicated, can be described with a pair of numbers. The first number is what we call the x-coordinate. That tells you how far left or right you go. This x line, so this number a could be 2, so then over here would be 1, over here would be 3. So that would say we have to go right 2, and then maybe that b is a 7, so then we go up 1, 2, 3, 4, 5, 6, 7. And again, I don't have these marked off individually because I haven't put any numbers to paper yet. We'll get there, don't worry. But this is something that you were supposed to have seen. This is technically prerequisite knowledge. But we will still kind of have a nice introductory phase to it. So again, in a pair of parentheses separated by a comma, you'll have two numbers. The first one tells you how far left or right you go. How do you know whether it's left or right? It's based on the sign. All the negatives fall to the left and the positives fall to the right. So if I just want to have a couple of random numbers up here, not random, could go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, but since we're going left, that's -3, -2, -1, then 1, 2, 3, and since we're going down, that's -1, -2, -3. So this point right here, to get there, you have to start at what we call the origin, the origination point, which is where the axes cross. So if you need to see that as a name, this point right here, where the axes cross, that is a terrible looking arrow. Let's try that again. That is known as the origin. And as a point, it's 0, 0, because you don't move left or right or up or down at all. So every point is relative to the origin. So this is our 0, 0. Think about how far left or right you go first. I gotta go right. 1, 2, 3. So in this pair of parentheses separated by a comma, the numbers that are separated by a comma, that is to say, we're going right 3. And then from this, we go up 1. So that point is 3, 1. That's how we can graph a point or tell the location of a point. You always need to think about how far left or right you're going first, and then how far up or down you're going. If you get them backwards, it's wrong. If you put negatives instead of positives or vice versa, it's wrong. You have to be careful and you have to pay attention. So in this QR class, one of the bigger issues we're going to have ultimately is looking for patterns with larger tables. Pay attention to how much the first value increases and how much the second value increases. So when I say first value, I mean the left ones, and when I say second, I mean the right ones. So if these are changing in a consistent pattern, you might be able to make a quicker conclusion about future data. I'm going to pause on this idea until we actually get into our guided worksheets, but this is going to come up. Trust me, this is going to come up. So this is a great idea for time saving. Let's say you've got that situation where your boss asks you for 100,000 different bits of data, or a graph with 100,000 bits of data. And you notice, okay, well, every time the x value is just going from 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7, 8, 9, 10. It's going up 1 every time. And then maybe your y's go from 2 to 4 to 6 to 8 to 10. So every time the x value goes up 1, the y value is going up 2. And if this is consistent for a couple of points, then you can say it should be consistent for all points. This is the idea of proportionality. This is the idea of proportionality. In other words, if you double one thing, the other should double. That kind of idea. These patterns play into that, which is why the title of this section, which I haven't said until just now, is Proportionality. Everything dealing with lines is a proportion. All lines are proportions. They are directly proportional. So that means if you double the x value, the y value should double. Asterisk, asterisk. This is the idea of proportionality, except one minor detail. Remember how we said with temperature, those weren't proportional because 0 and 1 didn't necessarily mean 0 and the other? The same thing is true here. So while the basis of lines are proportions, if they don't start at the origin, they aren't actually, but it's still a similar idea. You can say that if one thing changes in one pattern, the other thing should change in another pattern. That's why I say it's the basic idea, but not exactly the same. It's not always if one doubles, the other doubles. And we will see that. Okay, so we're just kind of checking a few things off of the important memos until we get into actually seeing some graphs and analyzing. You only need 2 points to form a line. All extra points are really just for checking. So check this out. Here's a point, and here's a point, and here's the point. So I got 3 points, point 1, point 2, and point 3. Now, if I connect those dots, we make a line. This is a line. It does not bend. It's straight, so it's a line. You only need 2 points to form a line. Let's see if that's true. How can I tell if this is true? Let me just systematically remove one of these points and see if the same line is formed. And I'm hoping I can do this without messing things up. Nope, that was the wrong one. It's just, there we go. So if I erase point 1, look at that. If I just had these 2 points, I would still form the same exact line. I didn't have to see point 1 to make that line. Check this out. If I delete point 2, that was weird. Maybe I didn't click eraser. This is more challenging than it looks to get it precise enough. Come on. Come on. There we go. Got it. 17th try is the charm, right? So if I erase point 2, if I only plotted these 2 points, can you see that I would still graph the exact same line? I don't have to have the middle point. I could have the first and the third. I didn't have to have the first one. I could have the second and the third. All right, let's try this one last time. So if I get rid of the third point, do you think the line is affected? There we go, first try, look at that. So I'd plot these 2 points, and then I'd connect them with a straight line, and I'd still keep going with the same pattern. That third point is irrelevant. So that's what I'm talking about here. You are only absolutely at a minimum required to have 2 points to form a line. All extras are just for checking. Now, does that mean I would never ask you to graph 3 or 4 or 17 points? I could certainly do that. So if your homework questions ask you to plot 3 or 4 or 5 points, make sure you do that, not just the minimum of 2 points. Because if you only plot 2 points, yeah, you'll still have an accurate line, but my math lab's going to mark it wrong because you didn't do everything they asked for. What's important about this is in the real world, if something has a linear relationship, you're not necessarily just want to plot the 2 points that you find. You want to be able to see every single infinitely many points that would follow this pattern. That is the beauty of graphing lines. If you just look at things as numbers, you've got to see the hundreds and thousands and millions and billions of different numbers to really encompass all possible scenarios. Okay, so I see what happens when x equals 1 and 2, but what about when x equals 1.937423981222267? Well, you'd have to plug that number into your equation and find out the y value. Or you could just say, well, here it is. You can point at that 1 point whatever, and then you can see the height already represented. So this is definitely one of those, a picture is worth 1,000 words, or a picture is worth 1,000 data values, if you will. I'm trying to decide if I want to show this next bit yet. I'm going to say no. So I'm going to put it on the screen for a second. This linear equation can be expressed as a total amount, a variable amount plus a fixed amount. We'll get into that next. But let's go to our guided worksheets for now. Guided worksheets. Here we go. Too much. So chapter 5, linear functions. So chapter 5 is on lines. When we get to chapters 6, I'm trying to remember which one we skipped. 7, we skipped 7. So chapter 6, 8, and 9, we go away from lines and we start getting to curves. Now lines are a great start to modeling in math, but a lot of things in the real world that can be modeled using lines on a small scale, you need curves on a larger scale. And I like to talk about the population of people, either in the world or in just our country, as a wonderful example of this that we'll see in the chapter. But let's not, again, put the cart before the horse. I don't know why I've got that phrase stuck in my head today. So blah, 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 blah. We've talked about ratios and proportions. We've already kind of discussed the idea of how linear functions are in the same realm as proportions. Sometimes they are literally proportions, but sometimes it's just they're pretty close to them. So in this chapter, we will study another aspect of proportionality, the fact that graphical representations of a proportional relationship is linear. Table 5.2 shows the cost of monthly track phone plans as proportional to the number of minutes talked at rates of 5 cents and 7 cents per minute. Excuse me. So we got ourselves burner phones, and we got ourselves 2 different burner phones from 2 different companies. One burner phone from company A, one from company B. Company A says, we charge you 5 cents a minute. Company B says, we charge you 7 cents a minute. Now, any QR student, if this is just all you're paying for, should immediately know, forget the 5 cent one. I'm sorry, forget the 7 cent one. I'm trying to say too much at once. Forget the 7 cents per minute plan, because why would I want to pay 7 cents for 1 minute when I could pay 5 cents for 1 minute? And if it's cheaper for 1 minute, it should be cheaper for 2 minutes, and it should be cheaper for 3 minutes or 10 minutes or 100 minutes. If this is all you're paying, if it's just a simple, oh, you're paying per minute or per text message or per whatever. 5 is less than 7, I'd rather pay 5. Hopefully you do too. So from table 5.2, we created the graph they call an XY scatter plot. Scatter plot, graph, same thing really. We use the phrase scatter plot a lot for Excel in figure 5.2. So that's all this down here, which gives us a visual display of the relationship between the inputs and outputs of the functions, noting that the points of each function all fall on a straight line starting at the origin. The rate 5 cents per minute gives us a measure of how steep the line is. The 7 cents per minute gives us also a measure of how steep it is, and we see that it's steeper. And this greater rate of incline, this is what we refer to as slope. Let's pause on that idea for now. So there's a lot of things that we don't need to talk about quite yet in this last couple of sentences. Let's get to the main idea here. And I don't necessarily like how they do this table right out of the gate. So this right here is one pair of values. So the minutes are our X and the cost at 5 cents per minute. That cent looks really odd right now. It almost looks like the pound symbol. Weird. Oh well, doesn't matter. So this is one table of values. So that's a table of values. And we say that if we talk for 0 minutes, we're going to pay 0 cents. I hope that makes, sorry for the pun, sense. Because if you don't talk, you don't pay. If all you're doing is paying per minute of messaging or whatnot. But if you were to talk 1 minute, well, they said it's 5 cents per minute. 1 minute times 5 cents per minute, the minutes would cancel and you'd get 5 cents. there's that idea of just multiplying and dividing things and canceling appropriate units. But I think that most of us should understand that, okay, you just take the number of minutes times the cost per minute. That is very, very similar to all the ideas in chapters 1 and 2 and 3. If you were to talk 2 minutes, well, you're going to pay 5 cents for the first minute and 5 cents for the second minute. 2 times 5 is 10. If you talk 3 minutes, you pay 5 cents for the first minute, 5 cents for the second minute, 5 cents for the third minute. 5 times 3, or 5 plus 5 plus 5 is 15. Again, these are in cents, not dollars. So this X and Y, I wish I had done that in blue. I'm going to undo all of that. I didn't realize that the graph was in blue. I should have. I should have thought about that first. So again, TOV, table of values. So this blue line, 0, 0 is our first point. So again, there's 2 different ways to represent points. You can do this as a table of values as seen in this box, or as coordinate pairs. So then it's 1, 5, 2, 10, and 3, 15. So 0, 0, you go right 0 and up 0. So there's the first point. Then 1, 5, you're going to go right 1 and up 5. There's the second point. Then 2, 10. You start at the origin, you go right 2 and up 10, which is right here. Then 3, 15, you start at the origin, you go right 3 and up 15. And then once you have all those points plotted, so you plot the point, you plot the point, you plot the point, you plot the point, then you connect and extend. So I'm drawing a really poor line over this, and I'm going to erase in just a second. This is how we would normally do things. And then you say this pattern goes on forever and ever and ever and ever. So you put an arrow on the end signifying that. This is the QR type of problem I mentioned, where while a traditional math line, you're supposed to extend it both ways. This would be a more traditional graph. We're talking about real life things. We can't talk negative minutes on the phone. We are not going to pay negative cents for talking negative minutes on the phone. This isn't like you don't do something so you get paid for it. That would be very odd, right? So in a QR sense, there's no reason to do this extension, because that would mean we're going into the negative minutes if we actually draw the rest of this rectangular system. We're not going to pay negative cents. We're not going to talk negative minutes. This would not make any sense, which is why I said in QR, a lot of the times, all you're going to see is this portion of a graph, just the top right, the first quadrant, if you will, if you're familiar with that terminology. The first quadrant is just where everything is positive. Now, sometimes you'll deal with the first and fourth quadrant, which is where the X values are positive and the Y values can be positive or negative, because sometimes it could make sense to have a negative, maybe cost associated with it, or income or something like that. All right, so now let's do the other one. The red graph. How did this red graph get made? Well, they're using these minutes, that's the X values, and then this set of costs, these are the Y values. So this is just a table of values with multiple functions. So I don't like that this is the first thing they do, but it's not the end of the world. So now this red graph is based off of these is the X values, the minutes still, and this new value of cost, because now we're on the 7 cents plan. So those points would be 0, 0. If you talk 0 minutes, you're still going to pay 0 cents. But now if you talk 1 minute, you're paying 7 cents. Now if you talk 2 minutes, you're paying 7 for the first, 7 for the second, so 14. And if you talk 3, it's 21 cents. So here's your 0, 0. Then you go right 1, up 7. Now, I don't have 7 labeled on the graph because it just gets tedious for them to label every single number. So if you trace this back over here, this is the height. That looks like about 7. It looks like this would be about 6. This would be 7, then 8, and then 9. And you just got to get microscopic in size. It's tedious. It's annoying. So not every single height for these graphs or charts or scatter plots, whatever you want to call them, are going to be represented. This is very, very common in Excel, especially. All right, so then the 2, 14, you're going right 2, up 14. So if you trace this over, That's just below 15. That looks like a good height of 14. 3 comma 21, start at the origin, go right 3, up 21. Notice that the minutes, 1, 2, 3, there's these big leaps, but the cents, they're tiny leaps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 20. So these don't have to be scaled the exact same. 1 inch on the x-axis doesn't have to represent the same value as 1 inch on the y-axis. It's all about what's relative to the problem. All right, so when you plot those 4 points, you would connect them, and then you could extend it if you really wanted to. So this represents the pattern of paying 7 cents per minute. So with this line continuing on, I could just say, all right, well, I need to know what happens at 5 minutes. So I find out where 5 is on the graph. I take this thing over here, and then that tells me the output. I just got to find the respective height. I don't have to do any actual math. I can just use my eyes. So this is how graphing of lines tends to feel in this course. They don't have to start at the origin. Now, when they start at the origin, this is a proportion. Again, we are trying to tie graphing lines to the idea of proportionality, but they're not always proportions. If they start at the origin, it is a proportion, because if you double one, the other doubles. Just look at the minutes. If you double the minutes from 1 to 2, the cost doubles from 5 to 10, or the cost doubles from 7 to 14. So this is a proportion. I'm actually going to make that note on the other page. So let's clear our screen. Let's take off annotate. Let's go back to this. So again, oops. A line goes through the origin. It is a proportion. It doesn't just share a small concept of proportionality, it is proportional. Still holding off on that other note though. The extra notes, that is to say. All right, so back to the worksheets. Wish my Windows button worked. All right, guided activity 1. This worksheet connects the concept of proportionality and constant rate to linear functions. Please read through the first example that has been done for you and then complete the following 3 examples. So what we're going to do here is we're going to take one of the 2 scenarios we just dealt with, specifically the 5 cents per minute plan. But we're going to make this a little more realistic. Because with a real cell phone plan, I think that most of us know, you don't just pay a per minute or per text message rate. You have fees. Now in this world, admittedly, most cell phone plans don't even do that. Most cell phone plans have infinite minutes, infinite text messages. It tends to be the data where some cell phone plans have that cap. So this problem is a little archaic, but let's just go with it. Like I said, I like to relate this more to a burner phone. So they say that the cost you pay is proportional to minutes you speak at a rate of 5 cents per minute. So that's the first scenario. So when we're talking about the first scenario, we're specifically talking about this column, where these numbers come from. When we say that cost is proportional to the minutes you speak at a rate of 5 cents per minute, that means if you talk 0 minutes, you pay 0 cents or $0. If you talk 100 minutes, you'd be paying 500 cents. If it's proportional, you can just take the number of minutes times the rate. That's something we got into the idea of proportionality at y equals kx. Also, you could just cross multiply if you really wanted to have a setup with that. if 1 minute costs you 5 cents, then 2 minutes would cost you this, or 100 minutes would cost you that, cross, multiply, solve, all that good stuff. But 100 minutes would cost you $5 because that's 500 cents. 200 minutes would just be the 5 times 200. So again, those numbers, it's 100 times 0.05 because that's how we represent 5 cents, and that would be $5. The 100 times the, 200 times the 0.05 gives you our $10. The 300 times our 0.05 gives us $15, et cetera, et cetera. 400 times 5 is 2,000, 500 times 5 is 2,500, so that's $20 and $25. So this right here would represent one line. And you see a little bit of a blue line, that's not it. We'll scroll down in a bit. So this would be one set of data to make a line with. Oops. Next, so in blue. Next, assume there's an additional fixed cost of $20 each month. That is how these numbers are achieved. Let's see how those numbers are achieved. A fixed cost. So we're going to get into this officially in just a few minutes after this example. Fixed cost means it doesn't change. Variable cost means it does change. So a cost being proportional means it's changing, it's variable. Fixed means it doesn't change. It's stuck. Kind of like a fixed cell reference doesn't change the cell. So if you have a fixed cost of $20 each month, it doesn't matter if you talk 1 minute. It doesn't matter if you talk 5,000 minutes. It doesn't matter if you talk 2 million minutes. It doesn't matter if you talk 17.5 minutes. You are going to pay a flat fee of $20. This is kind of like rent. No matter how much electricity you use in your apartment or your home, your rent isn't affected by that. Now, I'm going a true actual rent. If you have a landlord who says, all right, you're just paying all this no matter what, that could be funnier, so we have to ignore those weird situations. So these are your fees. Okay, you're going to pay $19.95 for your infinite minutes, but then you got to pay your taxes and this and that, and those are your fees. You pay this flat amount no matter what. So this is in addition. It's not just, oh, you talk 0 minutes, you pay $20. You talk 5,000 minutes, you pay $20. You talk 2 million minutes, you pay $20. You're not just paying that $20. You're paying it in addition, and that phrase is very important. You're paying it in addition, which means you're adding it, to the variable cost. You have two primary types of costs in the world. You have your fixed costs and you have your variable costs. Fixed doesn't change. That's your rent. Variable costs do change. That's your electric bill based on how much electricity you use, or your gas bill based on how much gas you use. Things like that. So what we're going to do is for each of these scenarios, when we talk 0 minutes, when we talk 100 minutes, etc., we just take the variable cost, which were the ones in the red circle, and we add the fixed cost. So if you talk 0 minutes, you're not paying anything in terms of minutes, but you are going to pay that $20 flat fee. So you pay your $0 for your minutes and your $20 for your fee, meaning you now pay $20. If you talked 100 minutes, hold on a second, sorry. Sorry about that. Okay. So if we talk 100 minutes, we said that we got to pay that cell phone company $5 for our minutes. But we also have to pay that cell phone company our $20 in fees. So $5 for our minutes, $20 for our fees, means that we are paying $25 in total to the cell phone company. We're just adding the variable cost, and the fixed cost. That's why this column is labeled as cost plus 20, the variable cost plus the 20 flat. If you talk 200 minutes, you have your $10 that you paid in minutes plus the 20 that you pay in fees, which gives you $30 that you're actually paying. When you talk 15 minutes, add your 20, you're really paying 35. When you paid 20 bucks for 400 minutes, add your $20 for your flat fee, and you're really paying 40. When you talk 500 minutes, that comes out to $25 for your minutes, plus the $20 fee, making it $45. All right. So, all of that data boils down to these two lines on our chart here. The blue one being the right values and the red one being the middle values. So let's recolor those in. So the blue one was these, and then the red one was these. Okay. Now, of course, these are the X values for both of those. So the minutes are always how far left or right we're going. And there's no real reason to go left because, once again, we can't talk negative minutes on the phone. So let's see how this red line was graphed. 0 minutes, $0. So that's this point right here. We don't go left or right at all. We don't go up or down at all. Then 100 minutes, $5. 100 minutes, $5. So we go right 100 and we go up 5. So there's our $5. So there's our first point. Then 200 minutes, $10. So when we talk for 200 minutes, we pay 10 bucks. 300 minutes, we pay 15 bucks. So right 300, up 15. And then you can see that the chart didn't actually plot the 400 and the 500. I could extend this if I wanted to, but the idea is good enough. So that 400 is probably, let's see, that's a height of 20. So that's going to be about here. It's not going to be perfect. And then the 500 comma 25 is probably about here. And again, you could extend this if you really wanted to. I'm not worried about that though. And then you connect those dots, in a linear fashion as a line, if you will. And there you go. And once again, you could really extend this, which was basically what I was trying to show. So again, the power of this picture is, well, what happens if you talk 250 minutes? What happens if you talk 250? So now I got to do the math. 250 times my 5 cents per hour. Well, no, instead of doing that, I can just say, here's 250 minutes, find where that point on the graph is, which is right here, trace that over, and if you have a nice ruler and everything, you could see that that height was there, which is exactly halfway between the 10 and 15, and that would be 1250. Or if you have graphing technology at your fingertips, like Excel or just a calculator, then you can use that to manipulate it, and you don't have to just visually figure out where that is. You can use the program. You can just type the number and boom, it'll give you the 1250. Or maybe I want to know what happens at 249 minutes or 203 minutes, excuse me, or 122 minutes. Again, this picture is able to accurately represent all of these heights as long as you either have a very, very, very good ruler and eye or technology at your fingertips. All right, these vertical black arrows, I'll explain that in a few minutes and why this really shouldn't be here. This is nothing you'll ever do on the homework or on a test. It's just trying to give visual flair to something. So after that, let's go to blue. Now let's graph these. So again, we're still using the minutes, but now we're using the right cost values. This is accounting for the variable and fixed cost. So that's 0 minutes, you're paying $20. So you go left or right 0 and up 20. So here is that first point. The 0 minutes is $20. Or if you talk 100 minutes, we came up with a $25 cost after the fixed fee. So you go right 100 and you go up 25. So there's our second point. If you talk 200 minutes, you're paying 30 bucks. So go right 200 and up 30. If you talk 300 minutes, you're paying 35 bucks. So right 300 and up 35. Then you connect and extend. Again, there's no real reason to move this left because we can't talk negative minutes, so that's why we don't see that on the graph. I really wish that they would extend this like so, but it is what it is. And again, you could still plot the 400, 40 and the 500, 45. But this is good enough. All I really needed to plot was 2 of these points because of the linear fashion. But if you don't know they're a line, you should probably plot 3 or 4 or 5 to make sure that it's a line, if you get what I'm saying. If you just have a pair, 2 pairs of data and you're not sure if they make a line, get a third, get a fourth, get a fifth. Maybe they're a line, maybe they're not. So what are these black arrows representing? The black arrows, this is just representing the vertical shift, the price movement, the price adjustment from the fixed cost being the $20 fee. It's just saying, hey, you paid $0 for your minutes, but because of the fee, that brings it up 20. You paid $5 for your minutes, but then you have your fixed cost, which brings it up 20. You paid $10 for your minutes, but then the fixed cost brings it up 20. You had paid $15, but your fixed cost brings it up 20. Again, these black vertical arrows are not something that I prefer people to draw. You're not going to have it in your homework. You won't have it on any review. You won't have it on a test. And again, this is chapter 5 material. This will not be on the midterm. Midterm's only up to chapter 4, up to and including chapter 4. So the red line is a proportion. It's a proportion because it starts, it has a point at the origin, 0, 0. The blue one is not a proportion, but again, it still shares a lot of the same basic premises of proportionality, but it's more about the change of one related to the change in the other. You can't just say if you double one, the other doubles. You have to say if one of them changes in a doubling value, then the other should change in a doubling value. So again, it's a shared idea, but just a little different. And we'll get into all of those details sooner than later. So this is the premise of this guided worksheet. We're going to end up graphing 2 lines, one for no fixed costs, another with a fixed cost, and that's pretty much it. So let's clear our screen. Let's go to the next example, one that's not actually completed for us. Weight of water. The weight of water is proportional to the volume at a rate of 8 pounds per gallon, and this is true. Water weighs 8 pounds a gallon. So if you have 1 gallon of water, that would weigh 8 pounds if you put just the water on a scale. Or if you had 2 gallons of water, that would weigh 16 pounds. Or if you had 3 gallons of water, it would weigh 24 pounds. And that's proportional. If you double one, the other doubles. But can you just put water on a scale? No, you can't. Yes, I can, Mr. Beckner. Just pour it in a glass and then put it on the scale. And there's your problem. You poured it in a glass. The glass weighs something. Okay, well, Mr. Beckner, I've worked at the meat place or whatever, some packing place. So you just tear the scale. You put the container on the scale. You zero it out, or tear it, not break as in rip. Tear, T-A-R-E, means to zero your scale. And then you pour your water in and everything's fine. Okay, yes, that is true. But we're going into a situation where the scale isn't teared. So assume that the bucket you were using to carry this water weighs 10 pounds. That's a heavy freaking bucket. I don't have any buckets that weigh that much. So it's a gold bucket or something, or an iron bucket. Me, I've got plastic buckets for my water, but that's me. But doesn't matter, point of the problem. Fill in the table for values of both functions. So what they are saying here is that the first column is ignoring the bucket. The second column is no longer ignoring the bucket. So, annotate. Let's do red. So this is no bucket. And then this is with. If you have 0 gallons of water, well, that's going to weigh nothing, 0 pounds. If you have, I'm actually going to skip to 0.5 and go do the wholes first. If you have 1 gallon of water, well, they said right here, it's 8 pounds per gallon. So that would be 1. If you don't believe that, you're 8 pounds per gallon times the number of gallons, which is 1 gallon. Your gallons cancel and you get 8 pounds. The 2 times 8 is 16. 8 pounds per gallon times 2 gallons. Your gallons cancel and you get 16. And I don't know why I wrote a 1 here. I said 1, that was 8. Talking and writing at 3 different speeds, always fun. Eight, 8, 8, and then the 2 was the 16. All right, so this column we said is proportional because of the 0, 0. So if you double one, the other should double. That also works backwards. If you half one, the other should half. So you could use that idea and say, all right, half a gallon should be 4 pounds of water, or you could use the idea of dimensional analysis. 8 pounds per gallon times 0.5 gallons. 8 times half is 4. The gallons cancel, so we get 4 pounds. 1.5, if you take 1.5 times 8, you're going to get 12. I'm not going to show the math for all these. If you take 2.5 times 8, you're going to get 20. So we could then go and plot these. I'm going to go ahead and do that. I don't want to fill out the table. Let's go ahead and start plotting them. So 0, 0, that's the origin. And they have they have the blue and the red swapped. That's okay. That's not going to matter after this. Then the 0.5, 4. So we go right 0.5 and we're going to go up 4. So that's right here. Then the 1, 8, that's right 1 up 8. Right here. 1.5, 12, that's right 1.5 and up 12, which is right here. They actually did this super convenient, so all these points are in the corners, so I bet you the next 2 are here and here. Then 2, 16, that's right 2 up 16, yep. And then 2.5, 20, we can go right 2.5 and up 20. Then we can make our line, connect and extend it, and I will extend it past these points. I'm doing my best to make this straight. I'm not an artist, as you know, and with the drawing tablet I can't even look at. It's impossible. I shouldn't have gone off the chart. There we go. So there's our line to the best of my ability, given my circumstances. So that again represents the no bucket scenario. Now let's do the bucket. Let's account for the bucket because we can't just put the water on our scale. We got to go grab our 10-pound solid iron bucket and then put water in it and then maybe not drink from it since it's iron. So now when we have no water, all we have is the bucket. The bucket weighs 10 pounds, so that's 10 pounds. All we're doing is adding 10 to every previous value. When we had 4 pounds of water, add 10 for the bucket, you get 14. When you have 8 pounds of water, add 10 for the bucket, and you get 18. This is extremely simple. When you had 12 pounds of water, add 10 to get 22. When you had 16 pounds of water, add 10 to get 26. When you had 20 pounds of water, add 10 to get 30. So now let's plot these as our x's and y's. So again, how far we go left and right is still based on the first column, but now how far up and down we go is based on the last column. So 0, 10. So we go left to right 0 and up 10. Now 10 is not marked. They even gave you a little hint right here. It's halfway between 8 and 12. 0.5, comma 14. So we go right a half, and we go up 14, which is also halfway between 12 and 16. 1, comma 18. So we go right 1, and you guessed it, up 18, which is halfway between 16 and 20. There's a pattern here. These first 2 points, because these were a line, and I'll explain how I knew that in a few minutes. But now that I can see these keep following the same pattern, I could extend and just keep going, but let's plot them all. Next, we got the 1.5, comma 22. So right 1.5, up 22. 2, comma 26, so right 2, up 26. 2.5, comma 30, so right 2.5, up 30. Connect and extend. Make this as straight as possible. Hopefully it's a little easier for y'all. This is not easy for me. And we say good enough. And again, I like to extend just to signify that the pattern goes on and on forever and ever and ever. And again, this is with the bucket. We can see that all the blue points are higher than the red ones. That is because the bucket has weight. The bucket is making everything weigh more. So height is how you can tell size, because all these blue points are higher than their respective red values. We can tell that it weighs more to have the bucket than it does without. And I know that should just make absolute sense without having to say it, but these aren't always super sensible problems that make sense. And again, what the textbook does is it draws these vertical black lines that I'm going to erase in a second. This is just saying, hey, the bucket causes it to go up 10. The bucket causes it to go up 10. The bucket causes it to go up 10. This is what a fixed cost does. The bucket causes it to go up 10. Again, not my favorite visual flair. If you like it, you can draw it on your own. But again, because it's not really something you see in homework tests, I don't want you to get used to it. Before we move on to 3 and 4, I mentioned something in the notes, and I'm not going to be able to pull it up without all this nonsense. I don't want to erase this stuff yet because I want these numbers. And in the notes, it said to look for patterns with larger tables of values to identify if this is a linear relationship. So this is what we're going to segue into now. Notice that these, for this first column, we're always going up a half. So to go from 0 to 0.5, we went up 0.5. To go from 0.5 to 1, we went up 0.5. To go from 1 to 1.5, we're going up 0.5. To go from 1.5 to 2, we're going up 0.5. This pattern is consistent. We keep going up a half, up a half, up a half, up a half, up a half. The next one you'd probably think is going to be 3, then 3.5, 4, 4.5, 5. There's a pattern. So every time these x values, the inputs, the independent variable, the V in gallons, whatever you want to call it, volume, every time those go up a half, let's see if we can find a pattern in the y values. So in the reds, how much did this go up from 0 to 4? It went up 4. 4 to 8, it went up 4. From 8 to 12, it went up 4. From 12 to 16, it went up 4. Every single time the left values go up a half, these right values are going up 4. This is what I mean by look for a pattern, because what if I then come in and say, all right, well, what happens at 3.0? Do this right now. You should be able to really quickly say, all right, well, since that went up a half, I expect this pattern to continue over here, so this should go up 4, meaning that the next one would be 24. I don't have to do the 8 times 3 or whatever funky number it might be. I can just say, all right, as long as the pattern on the left continues, the pattern on the right continues. So the next one would be 3.5 on the left, and the next one on the right would be 28. And then it would be 4 and 32, and then 4.5 and 36, and 5 and 40. That's the pattern recognition I'm getting at. That's where the idea of proportionality is lent, even if it isn't a proportion. Now, yes, the red one was a proportion, so let's see if that holds true with the blue stuff. So the independent ones, the volume, they're still going up a half. Let's see what happens to these blue values, what happens every time. Going from 10 to 14, we go up 4. Going from 14 to 18, we go up 4. Going from 18 to 22, we go up 4. From 22 to 26, we go up 4. So if the next one is this 3.0 gallons, we'd expect to go up 4 from the previous one, so that would be 34. Then the next one would be 38, then 42, then 46, as long as we keep going up a half a gallon at a time. Once again, this is where the idea of proportionality is shared. If you increase the same amount in one, the increase in the other thing should be the same as well. I'm not saying these values match. They're different, 0.5 versus 4. I'm saying if you keep changing one thing in the same pattern, then the other thing should change in its own same pattern. So this pattern recognition would help you to just keep railing through these without continuing to have to do all this math if you're showing your work. Sorry, I keep saying my internet connection's unstable, so I'm afraid that my mic is going in and out. I have 2 people working from home here, and if they're using Zoom too, things get funky. All right. So let's clear our screen. Let's take off annotate, and I'm just going to point out on those notes, even though I said it 50 times, what I was referring to. Look for patterns with larger tables. Pay attention to how much the first value increases and how much the second value increases or decreases, because it could be going down. If this is consistent, you may be able to make quicker conclusions about the future data. That's exactly what we were just discussing. Okay, back to the worksheets. And this one's on 2 pages, so I'm going to have to make this one kind of small to be able to get everything. Well, maybe I can just take the instructions off. Will that be good enough? Yeah, that'll work. Okay, but let's look at the instructions first. Buying tickets. The cost is proportional to the number of tickets you buy at the fair at a rate of $2 per ticket. So if it's, let's say, 1 ticket for each ride, which is not how fairs usually work, but let's just keep it simple. Then you're paying a flat $2 per ticket. There's no bulk option where you buy 10 tickets and it only costs you, I don't know, $15, something like that. None of that. Simple. So $2 a ticket. So if you buy 1 ticket, you're paying $2. Buy 2 tickets, you're paying $4. Buy 3 tickets, you're paying $6. But that's only for your tickets. This is one of those places that also charges a fixed cost just to get into the fair. So it's $15 just to walk in the door and not even necessarily ride any rides. Now you might think that a lot of places like this don't exist. I'm going to argue that there are a couple of major ones in our state. One in particular, Busch Gardens. You might say, oh, well, you don't pay tickets. You don't pay money to get tickets to ride a ride at Busch Gardens. You pay your single ticket to get in, and then you go, okay, well, what's the other fee? Parking. A lot of people forget that there's a big, giant parking fee at Busch Gardens that seems to triple every single year. I'm exaggerating, of course. But anyways, just trying to liken it to something. So you're paying $2 per ticket, which gets you a ride, but it also costs you $15 just to get into the door. So maybe there's other things to do there besides rides. So if you buy 0 tickets, and let me get the color coordination right this time. They don't even do the other one, so I got to do blue for the first one. All right, so again, $2 per ticket, and then $15 is the fixed cost that we'll worry about later. So it's $2 per ticket. I just want to write that to the side somewhere. $2 per ticket, and then it's a 15 flat fee that we'll get to later. So if we buy 0 tickets, we pay $0. Again, ignoring the fee. If we buy 5 tickets, well, if it's $2 for 1 ticket, it's $4 for 2, it's 6 for 3, 8 for 4, and be 10 for 5. Again, if you don't want to do your math that way, you can say, here's your $2 per ticket. Remember, anything that comes after per goes in the bottom, $2 per ticket, times the number of tickets, 5 tickets, so that the units of tickets cancel. 2 times 5 is 10. We still have the dollars, so $10. So our tickets are going from from 0 to 5, which is an increase of 5, then from 5 to 10, which is an increase of 5, then from 10 to 15, which is an increase of 5, then from 15 to 20, which is an increase of 5. So let's see what happens in the blue numbers. Going from 0 to 10, we went up 10. How about from 10 to whatever this next one is? What do we go up or down? Let's see. So 10 tickets, that would be $2 per ticket times the 10 tickets. The tickets cancel. 2 times 10 is 20, so that would be $20. We went up 10 again. That pattern held. When we go up 5 in one thing, the other's going up 10. So that means I expect going from 20, we'll add 10, and it should be 30. Then we'll add another 10, and we'll get 40. Sorry, this is a little small. Then we'll add another 10, and we'll get 50. I don't have to keep doing the multiplication every time. I can just keep adding 10. But sure enough, 15 times 2 is 30. 20 times 2 is 40. 25 times 2 is 50. Let's go ahead and graph that line. So those are the points 0, 0, which is the origin, so that's right here. 5, 10, which is right 5 up 10. Not up 5, right 10. It's right 5 up 10. We have 10, 20, so we go right 10 up 20. And once again, these end up being on the corners. You could probably see the pattern by now. Since we're dealing with a linear relationship, you could just go ahead and probably draw your line, but let's do all of them. 15, 30, which is right here. 20, 40, and then 25, 50. Connect them as straight as you possibly can. Pardon your teacher and his drawing tablet. This is where the book would stop doing things. I like to extend, though, to show the pattern keeps going forever and ever and ever. I can draw this thing off the paper if I wanted to. So that is with the no flat fee. That's without your flat fee to get in. Now in red, we'll add that flat fee of $15. So just take the previous cost and add 15. So if you pay $0 for your tickets, you still got to pay your $15 fee. If you pay $10 in tickets, add your $15 fee, and you get $25. If you pay $20 in tickets, add your $15 fee, and you get $35. Now you could keep just adding 10 of the previous ones, or you could do that pattern recognition. All right, from 15 to 25, what happened? We added 10. From 25 to 35, we added 10. Well, look at this. The first values keep going up 5. These values keep going up 10. So you should expect that to continue to happen. Just keep adding 10 to the previous one. So from 35, you get 45. From 45, you get 55. From 55, you get 65. If you don't trust that, go to the blue numbers and add the 15, which was the fee. 20 plus 15 is 35. 30 plus 15, 45. 40 plus 15, 55. 50 plus 15 is 65. Does it matter which way you're doing this? No, ultimately. Does it matter that you have a way to be able to do it? Yes, that's the point. Once again, I don't teach this class just to say, this is the way you do it this way. I teach this class to say, if you can find a way to do something and it's always right, as long as you understand it, as long as you know how to use it, be my guest. I didn't just teach dimensional analysis as dimensional analysis. I said you could also do it as proportions, whichever you liked. Again, that's the point of QR. Teaching you that math is not just do it my way or it's the highway. Math is, man, a lot of times there's 10,000 ways to do something. You can look at things as an algebraic approach. You can look at them as a geometric approach. You can look at them as a calculus-based approach. You can look at them as all these different classifications of math that I'm not even going to throw at you. All right, so let's graph. So now we're graphing the t values, which were the number of tickets, against the cost with the fixed flat fee of 15 bucks, the red values. So 0, 15 is right here, halfway between the 10 and the 20 vertically. Then 5, 35, we go right 5 up 35. I'm sorry, 5, 25. Pardon my misspeak there. Then 10, 35. Then 15, 45. Then 20, 55. And 25, 65. Connect and extend with a nice line. Try and not bend it like I just did. That wasn't too great. Let's try that one more time. And then I like to extend just a little at least. So that was with the fee. In other words, your final cost. With your fees is generally your final cost. Okay. One thing I'd like to point out about this problem is what we call the slope. Let me do this with a nice bright green. So something that was mentioned in the notes previously was talking about slope. We didn't use the word slope, but I did relate it to that. Slope is the ratio of the change of the two things, the change in the horizontal versus the change in the vertical. So going between, let's just use the blue graph, going between these 2 points, this distance right here, that's terrible looking. This distance right here, this horizontal distance, that is 5. When we go from 0 to 5 tickets, so that horizontal distance is 5. This vertical distance, we went from 0 to 10. So 5 versus 10, 5 versus 10. Well, check this out. If I do that, another one of those little triangles anywhere else, if I do it right here, if we go from 15 to 20, the horizontal distance, that is 5, an increase. And then you're going from a height of 20 to 30. That's a change of 10. If you do it on the red one, look at this. If I go right from here to here, that's going from 5 to 10, that distance is 5 long. If I go, and then the up, I'm going from a height of 25 to 35, which is 10. These little right triangles are exactly the same each time. We're going right 5 up 10, right 5 up 10, right 5 up 10. That's represented with the black, blue, and red ink. The black ink here are the rights, the right values, we're going right 5, and then the blue or the red, we're just going up 10. This is how we talk about slope. Slope is the ratio of the vertical change to the horizontal change. So we can see that these lines, both lines, have equal steepness. Which is known as slope. We go right 5 units and up 10 to get to the next point. That's what we call the rate of change. Slope, rate of change, steepness, those are all interchangeable terms that we're going to study. So the point being, the fee doesn't affect the slope. The fee doesn't affect the steepness or the rate at which you're paying. It's just an addition. That's why we kind of diagram the fee as that vertical distance. This vertical distance represents the fee, the flat fee of 10 bucks. And you can do that anywhere. You can do that anywhere. That's the fee. And then the slope here, this represents your rate. And these are all 5s and 10s. Check this out. If you take the ratio of them, slope, and again, you'll have this written out a little more formally later. It's the ratio of the vertical to horizontal changes. And for every single one of these little triangles that we drew, the vertical change is 10, 10, 10. The horizontal change is 5, 5, 5. So that's 10 over 5. And guess what 10 over 5 is? 2. Guess what our rate was? 2. It is not a coincidence that these numbers match. The slope is your rate. So the cost that they give you as a per something, that represents the slope. That fee, the flat fee that's not based on how much of something you do, that represents what we call a vertical shift, or what we can call a y-intercept, as we'll get to. Clear screen. Let's scroll down. Let's do one more of these. So I'm trying to get this set up perfectly. There we go. Driving distance. The distance you drive is proportional to the time driving at a constant speed of 40 miles an hour. So if you get on the highway and you stay in the right-hand lane because you're only going 40 miles an hour, or you just end up on a road with no stoplights, no traffic, nothing, and you're just going 40 miles an hour and you're never changing your speed. This is a true statement. And the distance you drive is proportional to the time driving. Since it's proportional, that means you can just multiply something out, use fractions and cross multiply, whatever. I've just been kind of doing it the dimensional analysis way to keep it basic. Next, assume the distance driven includes the 100 miles you already drove. So you've been on the road for 100 miles and you just realized, well, dang it, when I filled up at the gas station, I forgot to click my tripometer, a little button that says, oh, okay, you're now on 0, so you can use that to measure your fuel consumption if you want to do a little division, or just know how far you've gone for a particular tank of gas, whatever. Doesn't even have to be based on a tank of gas. You can just do it based on a trip. So we drove 100 miles before we realized, well, shoot, I forgot to reset my trip, and then you hit the button. So we'll account for that later. For now, fill in the table. Let's just do the distance ignoring that 100 miles. So just accounting for the 40 miles per hour. So again, we'll do this in blue. Blue. So if you drive for 0 hours, how far do you go? Well, you go 0 miles. If you drive for 1 hour, well, they said it's 40 miles per hour, so hopefully you understand that that means you'd go 40 miles. If you don't, take your 40 miles per hour and multiply it by 1 hour, so the hours cancel, and you get 40 miles. Now, let's look at the independent values, 0, 1, 2, 3, 4, 5. They're always going up 1. This is up 1, this is up 1, this is up 1, this is up 1, up 1. So if we can find a pattern on the right side, then we could keep just using that pattern instead of having to keep doing this math. So from 0 to 40, we went up 40. Let's see what happens if we go to the next one. How much do we go up? So if we drive for 2 hours, that's 40 miles per hour times 2 hours. The hours cancel, 40 times 2 is 80, so we get 80 miles. That went up 40, so there's a pattern. Since the x values keep that their pattern, the y values should keep their pattern, so the next one should go up 40. So it'd be 120. The next one should go up 40, so 160. The next one should go up 40, so 200. And you don't have to do it that way. You could keep just doing 40 times 3, 40 times 4, 40 times 5. You'll get the same answers. I don't care which way you do it. Let's plot them. 0, 0, 1, 40, 2, 80, etc. Here's 0, 0, 140, 280, 3, 120, 4, 160, 5, 200. I'm going to go a little quicker with this one. Connect and extend. Boom. There's our line. And that would be without the reset on our tripometer. So this is not accounting for the 100 miles we already drove. So again, the way I've kind of rationalized this is without the trip reset. So it feels like 5 hours. Our trip now says 200 miles, but in reality, we know we went those other 100 miles. So we got to account for that. So now that's what we do, account for the trip. So the trip had 100 miles on it before we reset. So add 100 to all these values. 0 plus 100 is 100. 40 plus 100 is 140. 80 plus 100 is 180. If you don't like doing it that way, you can look for the pattern. Going from 100 to 140, that increased by 40. Going from 140 to 180, that increased by 40. So 180 plus 40 should be 220. If you add another 40, you'll get 260. If you add another 40, you'll get 300. Or I could have just taken the 200, added the 100 from the trip to get the 300. Do it either way. All right, so now it's 0, 100 for the first one, which is about here. Then it's 1, 140, which is here. 2, 180. 3, 220. 4, 260. That's an ugly looking 6, isn't it? Let's just make that a little better. And then 5, 300. Connect and extend. Sorry, I went off that last point, but you get the idea. So that was the actual trip mileage. How far we've actually gone. Even though our tripometer says after 5 hours we've gone 200 miles, we know we went that other 100 miles because we hit the reset button. So you have to pay attention to that. So again, the fact that it was 40 miles per hour, that was a rate. Because of the word per, when we see the word per, that's a rate. We are equating rate to slope. This is also known as the variable amount of the change. I'm not using blue and red to signify these two graphs. I'm just using it to signify different information. The 100 miles, there's no per, so that's not a rate. That's the fixed amount. The rate is the variable amount. How do you know it's a rate? Because it has the word per. The fixed amount is the thing that doesn't have a per. So let's take that and get into the next bit of our notes finally. There it is. I forgot I moved this thing. I hit clear screen. Thought I did. I gotta find out how to make that stop popping up twice at a lecture. It's weird. Okay. Boom. Linear equations can be expressed as a total amount is the sum of the variable amount and the fixed amount. So let's just do this part right now. Linear equations can be expressed as a total amount is equal to the sum. How do I know it's a sum? Because plus sign. Let me just put this all on the same line. The total amount is equal to the variable amount plus the fixed amount. So variable amount is the amount we paid for tickets, or the amount we drove before the reset button was hit, or not accounting for the reset button being hit, I should say, or the weight of the water without the bucket, plus the fixed amount. The fixed amount was the thing that didn't change. That was the flat fee of $20 to pay Verizon or T-Mobile or whatever, or the bucket weight of 10 pounds, or the 100 miles that was on the odometer before we hit the reset button, the tripometer, excuse me. So the total is just a variable amount plus a fixed amount. You just add those two things. It's your rent, which is your fixed amount, plus your electric and water bills, which are variable. Just say they're balled up into one thing. Sometimes the fixed amount has a better name, though. Sometimes we call it an initial amount, and that just depends on the context. Fixed amount is sometimes a rent. That's not really an initial amount. Sometimes the fixed amount is that 100 miles that was already on the trip when you hit reset. That feels like an initial amount. So fixed and initial, those two words are kind of interchangeable. So if you see the word initial, that means fixed. Now, the fixed amount is just adding a number. Every single time we just added the 10, or we added the 20, or we added the 100, or we added the whatever it was, the weight of the bucket, or the 100 miles that was already on the tripometer, or the $20 for the fee. That's just added. There's no variable next to it. But the variable amount is called a variable amount because guess what it has in it? You guessed it, a variable. The variable amount is always a product. The variable amount is always a product. The variable amount is always a product. It's a product of the given rate, the $2 per ticket, or the $8 per gallon, $8 per gallon, excuse me, 8 pounds per gallon, or the 40 miles per hour. So that's the number for it, and then times a variable, whatever letter of you're choosing, X, M, C. It doesn't have to make sense. You can pick any letter you like. I'd say go with X if you don't want it to make sense, or use C or M or V if you want them to make sense, like V for volume or M for minutes, things like that. So this is usually like a Y equals AX plus B, where the AX combined, the A times the X, that's the variable amount, where the A is the given rate, the miles per hour, or the cost per ticket, or the pounds per gallon. The B, the thing without a variable, that's the fixed amount. So what we want to do is go back to the previous problems we just covered, and let's give them equations instead of just, throwing numbers around in the tables like we were doing, which was fine. Let's give them equations which could also be used to figure out what the final outcome would be. So again, this typical linear model can be expressed as a variable amount plus a fixed amount. So this is what all our lines look like as equations. A y equals ax plus b. Now this letter A, sometimes we call it m for slope because we said the variable rate is the slope. But we're saving that for the next section. So again, we're going to be writing equations like this. So something like y equals 3x plus 5. 3 would be the rate, 5 would be the fixed amount. Or y equals 2x minus 17. So 2 would be the rate and 17 would be the fixed amount, which would actually be like a bonus kind of because it's minus. They don't have to be x's and y's. They could be c equals 13m plus 1,000. So we got $1,000 flat fee and we're paying $13 a minute. I don't want that cell phone plan. I don't know about you. So let's see if we can do that. And the first one is, of course, pretty much given to us. And this is going back to the cell phone plan. And a lot of stuff up here is things I've already said. So when we were just talking about that we're paying 5 cents a minute, we're paying 7 cents a minute. So this right here this was before we had the flat fee. So we could just come up with equations that in cents, so these are in cents, FYI. The cost, 5 cents per minute times the number of minutes. So cost is 5 times M, where M represents the number of minutes. Or if you're paying 7 cents per minute, your cost is 7 times M. So these were not accounting for the $20 fees. If you wanted these in dollars, they would have been the cost is 0.05 times M and 0.07 times M, just FYI, and that's where this comes in lower. So each rate is associated with the constant of proportionality in the equation. Remember y equals kx? This is basically what we have here. Y equals kx, the number's the k. Y equals kx, the number's the k. So the slope is the constant of proportionality. So again, this is how we can write equations. You can use your words, you can use letters. In a QR class, it doesn't really matter. If it's a My Math Lab question, they'll tell you which one it should be. But in discussions and things like that, I wouldn't care if you're using words or letters. All right, well, what about the fixed fee? We also have that $20 fixed fee. So instead of just saying the cost, these are the variable amounts. This is a variable amount. This was a variable amount. So now they say, all right, let's just deal with the 5 cent per minute plan, but now let's account for the $20 monthly fee in addition. So the 5 cents a minute, this 5 cents a minute, the variable amount, you still see here, they wrote it second. It's kind of annoying that they wrote it second, but it's not a big deal. So this right here was the variable amount, 5 cents per minute times the number of minutes. But then here, this 20, that's your fixed amount. So your cost, your final amount, is the sum of a variable amount and a fixed amount. The fixed amount is just a number. The variable amount has the rate times your variable, which would have to be minutes, because it's based on minutes. And then finally down here, they just write it in a more appropriate algebra version. They actually put the variable amount first. So this 0.05 times minutes, they just put that first instead of second. The $20 is now second instead of first. And instead of writing the word minutes, they use the letter M. Instead of writing the word cost, they use the letter C, because these are easy to tell. C, cost, M, minutes. You could still write this as y equals 0.05x plus 20. So this right here and this right here are the same thing. But the problem is, when you have it in y's and x's, there's no sense of what these are. What is the x? What is the y? You need to write somewhere that x is the number of minutes and that y is the cost. If you don't do this, you are not doing what a QR student should do. If you just write y equals 0.05x plus 20, that's not good enough. You have to associate the variables with something somewhere. That way other people can pay attention to what you have and interpret everything correctly. Five seconds. Okay. So let us move on to the actual problems. Where, once again, the first real one is done for us. We already talked about that. And they use this little sub notation, which they didn't even put it on the first one, but they did on the second one. I don't know why they have to do it that way. It's whatever. Just ignore this little 2. Just ignore that little 2, please. So, cost is proportional to the minutes you speak at 5 cents per minute. Write an equation for this proportional relationship. All right, so cost equals 0.05 times the number of minutes, or you could instead write C equals 0.05 M, where M is minutes, C is cost, obviously. Now assume there's your additional flat fee of $20 each month. So this was the variable amount, you just add the fee. So here's your variable amount, add the fee, or C equals 0.05 M plus 20. Again, this was literally what we just did on the last page, which is why we did it so quick. Next up, weight of water. The weight of water is proportional to the volume at a rate of 8 pounds per gallon. So since this is our rate, and they even use the word proportional, this is what we multiply by the variable. This is the variable amount, the rate, but we have to give it the variable, of course. Write an equation just for that. So again, you could use y and x, but then you got to write what y and x are. Since we're talking about the weight of water based on volume, let's go W equals 8V. Now you have to be careful. Notice that this is not V equals 8W. You can't do it that way. Because this is 8 pounds per gallon, we have to multiply that by a number of gallons to actually get the weight. So 8 pounds per gallon times the number of gallons. If you do 8 pounds per gallon times pounds, you get pounds squared per gallon, which wouldn't make sense. So you do have to have these in the appropriate order. But there is another thing, if you remember about proportions from chapter 3, I said that you can write them either way. You could do V equals 1 over 8W, but it's not going to help you in the next step because you won't be able to adjust it, which is why I'm not going to write that. Now assume the bucket you use has that 10 pounds of weight. That's our fixed amount, so that's what we add to it. So we go W equals, you still have the 8V, which is the variable amount, plus the fixed amount, which is the 10. If you want to use your words, weight equals 8 times volume plus 10. So this equation could be used to find all of the values from, what example was it? 3? No, 2. From example 2 on page 193. You could use this equation to find the right-hand values, which were the 10, the 18, the 26, etc. All right, number 3. Buying tickets. The cost is proportional to the number of tickets you buy at the fair at a rate of $2 per ticket. So that's our rate. That's our variable rate. That's the thing that'll get a variable. Again, because it has the word per. And they use the word rate. And they use the word proportional, which means that's the thing that gets a multiplier. Those are 3 clues. So the cost is blah, 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 blah. So we're saying cost equals. Cost is means equals. We're talking about number of tickets, so let's call T the number of tickets. The multiplier is 2, so 2T. Where T is the number of tickets and C is the cost. And you can still write that. I think that would be nice to do, in fact. T is the number of tickets and C is the cost. I think labeling them with specific letters C and T, you don't really feel that's necessary. But if you label them Y and X, it is absolutely necessary. Now let's throw in our flat fee of $15 to get into the fair on top of our per ticket fee. So we're not going to multiply the 15 by anything, we just add it. So we get C equals 2T plus 15. That's it. Give you a minute to soak that in because I'm going to have to clear the screen. Last but not least, and I'll even write that last one up there. 2T, C equals 2T 15. Driving distance. The distance you drive is proportional to the time driving at a constant speed of 40 miles an hour. So no braking, no accelerating, no traffic, no pit stops. We're on the road. We're going, we're going, we're going. We got cruise control on. So 40 miles per hour because of the word per. We know that's the rate. Because of the word proportional, we know that this would be the rate, the thing that gets multiplied by a variable. It still has that kind of y equals kx stuff. It's just ultimately now the fixed number gets added in at the end. So we're talking about a distance, so let's go d equals, or distance equals, and then a number times a variable. Well, the number is clearly the 40 because that's the per. And we're talking about how many miles per hour, so this is based off of time. So you could use T for time, maybe you use the word H for number of hours, that would be okay. I like this one more though. Now assume the distance driven includes the 100 miles you already drove. So that's our fixed amount or our initial amount. So we just add it in, 40t plus the 100. And again, that equation can be used to get all of the right-hand values from problem 4 previously. And just the 40t could be used to find the middle values from the previous example. And again, I would normally do this as a discussion board. In fact, that was my original intention, to have 3 and 4 of both pairs of these examples to be discussion board problems. I was only going to do number 2 and then have y'all do 3 and 4. But because the midterm's coming up, I felt it was a little more I can't think of the word I want to say, relevant, important, whatever, to focus more on that stuff for now, because I know no one really wants to dive into chapter 5 too much too quick yet. But these ideas of being able to build these simple equations, to build simple graphs, to use these equations and graphs or table of values to extrapolate future data, very, very, very important for this kind of what-if analysis. And we've been doing things like this in Excel already. We just didn't have to build them from scratch. We were given the equation, kind of like the BMI formula. We were given that. We didn't have to build that. And that wasn't a linear formula. I would never expect anyone to be able to build that from scratch in here. But I do expect you to be able to build linear models from scratch as we have done. It's just a number times a variable and then another number being added. The way you tell which is based off of the language. The thing that goes next to the variable, the words per and rate and proportional are your clues to that. The thing that's just the constant doesn't have any of those. It's the includes the thing you've already done, or the fixed cost. I mean, sometimes they literally say the fixed cost or the initial amount. Do your reading, pay attention. All the clues are there. Now, in the real world, are all the clues there? Not necessarily. You might have to kind of dig and scratch at them, but you can find them ultimately. All right, so let's clear screen, take off of annotate, and that finishes 5.1. I'd love to go on to 5.2 and move on, but we only have about 15 minutes. We have the test coming up. I'd rather not start a section and just barely get into it, especially because it's almost test time. So let's go ahead and take a pause. We'll get into this stuff next time. Please read ahead. Please be prepared for this. We will be talking about this material on next class. So 5 days from now. Pull up your due dates and all the other information that's important just to close out. 4.2 is due on the 2nd, 4.3 and the 4 are due on the 7th. Your test is going to run from the 8th through the 10th. Now, because and only because the midterm is going to be going the 8th to the 10th, we finished 5.1 today, which means traditionally it's due a week later. But because that's due right in the middle of a test, I don't want you focusing your efforts on that. So I'm going to give you until Monday. And this is a weird one. I'm going to give you until Monday the 13th. So I don't usually do this. Monday, I'm even writing Monday because it's kind of weird. And again, by 11:59 p.m. So you'll have the Wednesday, Thursday, Friday to finish your test, and then you've got Friday, Saturday, Saturday, Sunday, Monday to do that one extra section of homework. Honestly, if you can, go ahead and get it done before you get to the midterm. I really don't consider this section to be super difficult, but that's not to say that you won't feel that way. But you have your instructional helps, your instructional aids to get you along the way. But you got an extended due date on that. No Excel due, no quiz due, discussion board. I'm going to put that midterm discussion up. Try and make it so, if you go in and post about question 2, if someone else wants to come in and ask about question 3, don't make it a threaded reply to the first person, make it, the next basic thing. If you want to go back and talk about what person one is asking, then reply to that specific one, just to keep things organized. So try and keep them threaded appropriately. All right, if you don't have any questions, we'll call it a day, get out a few minutes early, and we will see you on Tuesday. Quote, see you. Email me with any questions. Yeah. Have a good weekend.